Hi, welcome to our 20th lecture in Graduate Combinatorics. Today we'll talk about degree sequences of graphs. So we'll be concerned with the question that we stated during our previous lecture. If we're given a finite sequence of non-negative integers, let's say call them d1, d2, all the way up to dn, where n is some natural number. The question is there a graph gamma with vertex at v1, v2, vn such that the degree of the vertex vj equals the non-negative integer dj for any j between 1 and n. Now, the answer to this question, we'll see, it depends on what kind of restrictions we are going to impose on our graph gamma. So before we start discussing this in more detail, let's just give some simple examples to try to work out through this to get a better understanding of this problem. So let's say the first sequences that we have, let's say something like this, 3, 3, 2, 2, 1. So the question is there a graph which has 5 vertices? So in this case, n equals 5, and it has degrees 3, 3, 2, 2, and 1. Now the degrees, as you can see, they're all numbers between 1 and 3. And again, here, you can ask yourself, well, it depends if the graph has loops or it doesn't have loops, or if it has multiple edges. But in this situation, actually, the answer is only one, regardless of what type of graph we would like to get, and namely the answer is no. And the way we do that, this is a simple application of handshaking lemma. So during our previous class, we stated that the sum of the degrees of the vertices of any finite graph is even. So as you can see in the summation, you have 3 odd numbers. So because 3 plus 3 plus 2 plus 2 plus 1 is 11, that implies that there is no graph with this degree sequence. Now let's do one other example. So again, handshaking lemma, this example shows it can be used to give a negative answer to this question in some situations. Let's see another sequence. Let's try to do something very simple, 2 and 2. Here n equals 2. Now the sum of these two numbers, it's a very silly example, but the sum is even. So handshaking lemma cannot kill off this sequence. Now, you can try to construct such a graph. Now it depends on what kind of a graph we want. So if loops are allowed, then we can construct this graph, which has a loop at each vertex. So you have a vertex v1 and a vertex v2. And we mentioned last time that a loop contributes 2 to the degree. So degree of v1 equals degree of v2 equals 2. So in that case, if we allow loops, then the answer is yes. There is such a graph. I put it like this. If, let's say, loops not allowed, but we allow multiple edges allowed, then, so we cannot do the loops, but we can do the following. We can consider this graph. Let's call this, okay, we can also call them v1 and v2, and we can put a two edges between V1 and V2, and the degree in this case is also of each vertex is also 2, so that works. However, the last one is if we are restricting ourselves to simple graphs. So when we restrict ourselves to simple graphs, in this situation, if we have a graph on n vertices, the degree of any vertex V, let's say V1, has to be less than or equal than n minus 1, because the vertex V1 can only be adjacent to, cannot be adjacent to itself, and it can only be adjacent by at most one edge with any of the other n minus 1 vertices. So in this case, n equals 2. So we have that the degree of V1 would have to be less than or equal to 1. The degree of V2 would have to be less than or equal to 1. So that's not the case. So the answer here is no. There's no simple graph with a degree sequence 2 and 2. Okay. So this is a simple example that you can do by hand. But again, what I want to show you here is, so for the first part, that handshaking lemma can, it's maybe the first thing that you want to try if you're getting a sequence of these non-negative integers and you're interested in this question. You just see if the sum is even or odd. If the sum is odd, then there's no such graph. If the sum is even, then you have to do something else. And in example 2, we see that the answer depends if we allow loops. So that's kind of the most unrestrictive situation. And then we kind of restrict our conditions. We can say that we don't allow loops, but we can allow multiple edges. In this case, it doesn't make a difference. The answer is still yes. But then when we looked at simple graphs, the answer is no. There's no simple graph with degree sequence 2 and 2. So now let's look at this question in more details in general, and let's see what we can say. So the first scenario is where we have no restrictions on the graph that we're looking for. So that means that loops and multiple edges are allowed. So this is the first scenario. Okay, and in this case, actually, the result is quite perhaps not surprising, but is the following. So proposition, let n be a natural number, and d1, d2, dn be sequence of non-negative. There exists a graph. A graph, a gamma with vertex at v and edge at e, v equals v1, blah blah blah, vn, such that the degree of vj equals dj for any j between 1 and n, if and only if the condition is simple, if and only if the sum of j1 to n of dj is even. So in this situation where you allow loops and you allow multiple edges, the necessary condition from the handshaking lemma is actually sufficient for the existence of such a graph. So proof, well, one implication, so it's an if and only if statement, and the implication, let's in this direction, if there is, it's obvious, because if there is a gamma with the properties above, then by the handshaking lemma, what do we have? We have that 2 times number of edges
equals the summation from j equals 1 to n of the degree of Vj, which is the same thing as the summation from j equals 1 to dj, which implies that the sum of these integers is even. So that's very, very easy. Now, how about the other direction, the opposite direction? So assume that d1 blah, 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 dn, the sequence of non-negative integers such that the sum from j equals 1 to n of dj is even. So what we want now is we want to construct a graph with whose degrees are d1, d2, dn. And here's how we do it. There are no restrictions, so we choose the kind of the simplest way possible. So because the sum is even, it means, by a similar argument as in the corollary of the handshaking lemma from last time, if we denote by, let's say, k denote the number of dj's that are odd. So because sum from j equals 1 to n of dj is even, using the same argument as in the corollary of the handshaking lemma, we deduce that k is even. Now, without loss of generality, let's assume that let's say d1 blah 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 dk are odd, and the other ones dk plus 1 blah 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 dn are even. I mean, I didn't order them. We'll order the d's later on, but for now I didn't order them. So let's just assume label the first ones to be odd and the rest to be even. And again, remember that you have even, k is even here. Okay. And now how do we construct a graph? So here's how we're going to construct the graph. From the vertices that have even degrees, so there are no vertices yet. So from these d's that are even, I create the vertex vk plus 1 all the way up to vn. And here, I'm going to do, for the vertex vk plus 1, I want it to have degree dk plus 1. So dk plus 1 is even. So I do here dk plus 1 over 2 loops containing vk plus 1. So, and I do the same thing here. Maybe there are more, but I do dn over 2 loops containing vn. So clearly the degrees of vk plus 1 all the way up to vn equal dk plus 1 all the way up to dn. Now what do I do here? Well, so I do in the first part, I do the same. So for these vertices I create, for these degrees d1, dk, I create vertices v1 all the way up to vk. So let me see, v2 all the way, so vk minus 1, v2, and so on. And now, in the first part, now these d1s are not even, so they're all odd. So for d1, v1, I put there d1 minus 1 over 2 loops containing v1, and I do the same thing. So for v2, I do d2 minus 1 over 2 loops containing v2, and and so on, and the same thing for vk, and for vk all the way up to vk minus 1. We do the same thing. Now, at this point, the degrees of the vertices vk plus 1 all the way up to vn are the numbers that we want, but the degrees of v1, v2 up to vk, they're not quite the ones that we want. They're d1 minus 1, d2 minus 1, all the way up to dk minus 1 respectively. So what we do now, to make the degrees that we want, we pair up these vertices, and now here we use the fact that k is even, and so you can pair up these k vertices any way you like, but for example, you can pair up v1 with v2, v3 with v4, vk minus 1 with vk, and then you put an edge between each pair. So you pair up v1 with v2, all the way up vk minus 1 with vk. And now what we guaranteed, so from this construction, follow easily that the degree of v1 is going to be d1 minus 1, this that comes from these loops, plus that edge between v1 and v2, which is 1, which gives me d1. And similarly, you get that degree of vk equals dk. So this is, you have no, all the edges in this graph, well, almost all the edges of these graphs can be maybe loops. So you have, you basically, we took the simplest approach to constructing this graph because we had no restrictions. So we added loops at all the vertices that had, for all the degrees that were, for all the integers d1, dk plus 1 dn that are even. And for the odd ones, we added as much loops as we could, and then we added a pairs of edges between for these remaining vertices, v1, v2, all the way up to vk minus 1 vk. So that's a construction, and this proves this theorem. Okay. So here, no restriction allowed. The summation of the integers to be even is sufficient also for the existence of a graph. Okay. Now let's make it. Yeah, you know, it's not maybe the nicest result, but it's simple. So we answered this question. But let's do something a bit more more interesting. So let's say let's answer the same question. We have no loops, but we allow multiple edges. So in this situation, you cannot have a vertex adjacent to itself. So you cannot have this anymore, but you're okay to have multiple edges. Okay. So this is a result, guess it's in the paper of Hakimi that I posted on the Google Drive. And let's state it here. So Hakimi. So as before, let n be a natural number and d1, dn be a sequence of non-negative integers. There exists a graph gamma such that gamma has no loops, degree of Vj equals dj for any j between 1 and n, if and only if. Well, the first constraint is the same as before. Summation of j from j equals 1 to n of dj is even. But now we have extra restrictions, so we have another condition here. And so here, what comes into play, I need the ordering. For stating this result, I need these values to be ordered. So I order them this way, d1 greater or equal to d1 all the way to dn. In the paper, original paper by Hakimi, the indices are the other way around. So if you're reading that paper, please be careful. So the condition here is that the sum has to be even as before, like handshake lemma, and the other one is d1 has to be less than or equal than d2 plus all the way up to dn. And we'll see that in a second, where this condition is quite natural one. So and it's related to the fact that we don't allow loops. Okay, so proof. So this direct implication assume that there is a graph gamma with the above properties, then you can use the same this graph again, handshaking lemma as before. Handshaking lemma gives us the sum must be even. 2 times E equals summation of j equals 1 to n d of vj equals the summation from j equals 1 to n of dj, meaning that the sum from j equals 1 to n of dj is even. Okay, so that's clear. And where does the second condition come from? Now, Hakimi gives a proof by contradiction, but you don't really need a proof by contradiction. So what you can think of is, think about this vertex v1. So over here you have v2, v3, all the active vertices vn. Now, because of our condition with no loops, so we don't have anything like this. So v1 cannot be adjacent to itself, okay? So v1 can only be adjacent to maybe v2, or like can only be adjacent here. So they could have multiple edges, v3, maybe some vertex vj, multiple edges and so on. Okay, so if we look at the edges, each edge containing v1 is of the form v1 something else, vj. Okay, so if you look at the edges, the number of edges, let's say between, so here is j between 2 and n minus 1. So the number of edges between v1 and some vertex vj. So in this case, in this picture, you have 3 edges, but that number is less than or equal than the degree of the vertex vj, because again, here using the fact that the edge involves 2 vertices, 2 distinct vertices, v1 and vj. So the number of edges between v1 and vj is at most the degree of the vertex vj, because each of these edges is counted in the degree of vj. And now, if you look at if you sum up all the edges, so this is again for j between 2 and n here, not n minus 1. If you sum up the number of edges between v1 and vj for every j between 1 and 2 and n, so what do we get? We deduce that if you sum up all these number of edges, we get the degree of v1, and this is less than or equal than what? Well, this is going to be summation from j equals 2 to n of the degree of vj. So that's the proof in this case, because we do not allow loops, and so each edge involves 2 vertices. Okay. Now, okay, so that's the easy part. Let's do the other part. Let me use the other color. So assume, so we want to prove that these conditions, summation being even and d1, the largest one being at most the sum of the others, they are sufficient for the existence of a graph with no loops with this degree sequence. Okay, so for this part we will use induction. So we will use actually it's a strong induction on n. So we start with the first case. The first case is n equals 2. So the base case is n equals 2. And what are our conditions here? So we have that the sum of all degrees. So our conditions are that the sum from j equals 1 to 2 dj, which is d1 plus d2, this is even. Okay. And now our sequence was originally ordered d1 greater or equal to d2, but the second condition that we have is and d1 is less than or equal than the sum of all the rest, which is d2. So this condition in the case of n equals, if you combine the red and the purple, they give you that d1 must be equal to d2. Okay. So we're asking, okay, we have two non-negative integers that are equal. Can we construct a graph which has them as a degrees? And yes, that's easy to do. We just put here d1 equals d2 edges. There are no loops, there are multiple edges. So you could have, in this situation, you can have a graph. Let me go a bit crazy here. You can have a graph which has two vertices in which each vertex has degree 5, and there are no loops, and all these 5 edges go between the vertex 1 and vertex 2. And so this, the base case is correct, n equals 2. Let's do one more to see how it works for n equals 3. That will give us an idea about the general case. So n equals 3. The condition, I'll write it in purple, is that d1 plus d2 plus d3 is even. And the other one is that d1 is less than or equal than d2 plus d3. So you don't get this equality right away. So what we want now, we're asking, is there a graph where we have one vertex here, two vertices here, and three vertices here? And this one, we kind of go backwards in a sense. So how would such a graph look like in general? So a graph like this, what are the possible edges? Well, you could have something like, I don't know, x1, 2 edges here between 1 and 2. You could have x2, 3 edges here between 2 and 3. And maybe, I don't know, another, they don't have to be equal, but x1, 3 edges in here between 1 and 3. So what we're asking is, can I find actually, do they exist x1, 2, x1, 3, x2, 3 integers which are non-negative, so greater or equal to 0, such that what has to happen? Well, the degree of the vertex, so this is v1, v2, and v3. I would like the degree of v1 to equal d1, but what is for me degree of v1? It's x12 plus x13. I would like the degree of d2, which is dv2, to equal x12 plus x23, and I would like the degree of d3, the degree of v3, sorry, to equal x13 plus x23. So if you solve, go backwards, are there such integers? That's a good question. So if we solve this system here, what do we get? Well, we can add them all up. If you add them all these equations up, we're going to get d1 plus d2 plus d3 divided by 2 equals x12 plus x13 plus x23. And then you can pick each one at a time. So you can argue that x12 is going to be d1 plus d2 plus d3 over 2 minus, what do we want to subtract? I want to subtract d3, and x13 d1 plus d2 plus d3 over 2 minus d2 and x23 d1 plus d2 plus d3 minus d3. Okay, now, so these are the solutions. We don't know if they're integers and we don't know if they're non-negative integers, but our conditions are here about d1, d2, d3. The fact that the sum is even will tell us, will lead us to, so from here, because the sum is even, it will imply that each of these numbers, so x1, 2, x2, 1, 3, and x2, 3 are integers, because that fraction is going to be an integer. Okay, and now the other part, okay, d1 less than or equal to d2 plus d3. I think there's a typo here. This should be d1 here. So we want these numbers to be non-negative. So as you look at them, if we figure out that x23 is non-negative, then we are gold, because that should be the smallest one of all of them, because it has this sum. All of these variables x12, x13, x23 have the same quantity in the front, and then you're subtracting various dj, but d1 is the largest one of them. So let me check. So x23 equals d1 plus d2 plus d3 over 2 minus d1. And if you unpack this, it's exactly d2 plus d3 minus d1 over 2. But we know this from our hypothesis that this has to be greater or equal to 0. So all these numbers, x1, 2, x13, x23 are integers, and they are greater or equal to 0. So there is such a graph. If you want to do it on an example, let me give you a small example. Let's say that our sequence is 5, 4, 3. So n equals 3. And I have a sequence of, this is my degree sequence. And you see it sums up to 12, so it's legit. And I want the vertices v1, v2, v3. There are no loops allowed, so I cannot do the argument as before. So how does this work? Well, by our previous recipe, we get x12 is d1 plus d2 plus d3 over 2 minus d3. And how much is that? Well, their sum is 12, it's 6, minus d3 is 3, so it's 3. So that means that here I'm going to put, well, not here, here. I'm going to put 3 edges. And then you can do similarly, x13, so it's 6 minus 4 is 2. And I'll leave it to you to calculate x23 is going to be 1. So you put 1 edge here. And now you can check that the degree of v1 is 5, the degree of v2 is 4, and the degree of v3 is 3. Okay, so that's the base case. Now for the induction step, so for the induction step, so we assume that the purple conditions, the purple, conditions that sum j equals 1, dj even, and d1 less than or equal than the sum of all the others, are sufficient for the existence of our graph for any n, let's say, less than k. So let k be something greater or equal to 4 in our case. And let's assume that these conditions works for any, if you're trying to do k minus 1, k minus 2, all the way up to 2, these purple conditions are sufficient for the existence of the graph. Now we are dealing with the case n equals k, the case k, so let d1 greater or equal to dk be a sequence of non-negative integers such that summation j equals 1 to k dj is even, and d1 is greater or equal than d2 plus blah blah plus dk. Okay. So now I want to construct a graph with these degrees. So what we look at, we consider the following sequence. So let me use a different color. d1, I subtract from the largest one, I subtract the smallest one, d1 minus dk, d2 all the way up to dk minus 1. So here I don't put in front, I don't put greater or equal because I don't know if d1 minus dk, so here there's a mistake. This should be less than or equal. I'm sorry about that. So I don't know if d1 minus dk, where does it rank in this sequence of integers? But okay, before I do that, so this is a sequence. I have k minus 1 integers, but they're actually non-negative integers because d1 is greater or equal than dk. Okay, so that's I'm good there. Now, what is their sum? So if I look at their sum, so d1 minus dk plus d2 plus all the way up to dk minus 1 is, what is it? Well, it's the same as the summation from j equals 1 to k of dj minus 2 dk. But this one, from my hypothesis, this was even. And minus 2 dk is also even. So this sum is even. Okay. So what I want to do is I want to build a graph with this degree sequence, with this dark blue degree sequence. So I have that all the elements there are non-negative integers. The sum of them is even. So I have to check if the largest one of them is less than or equal than the sum of the other. So here I have two cases. So I have case 1, if d1, so let's assume for now that d1 minus dk is positive, and we'll deal with the other case later. So in this case, let's assume, so we're in case 1, d1 minus dk is positive, and we have subcase 1.1, in which we have d1 minus dk is the maximum, is the largest of all of them. So d1 minus dk is greater or equal than d2 all the way to dk minus 1. And what do I want to show? I'm interested in how is d1 minus dk compare to the sum of d2 plus all the way plus dk minus 1. Well, I claim that what happens here is that this is less than or equal than the sum, because it follows again from my induction hypothesis, from the inequality on the top of d1 at most d2 plus all the way to dk. If you subtract dk in each, so from that inequality subtract dk from each side, you get this one. So in this case, this satisfies the induction hypothesis property. But there is another subcase in which d1 minus dk is not the maximum, so maybe it's less than d2. But because d2 is the largest of all of the others, so in this case, d2 is the one that beats, d3 all the way to dk minus 1. So in this situation, what I want to check is if the condition involving d2, is it true that d2 is less than d1 minus dk plus d3 plus blah, 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 plus dk minus 1. And I claim that this is true here because of what? Why is this true? This is true because this follows from the fact that d1 is less than or equal than, d2 is less than or equal than d1, by the way I order them. And also the quantity here, we can do dk minus 1 minus dk is greater or equal to 0. So on the right hand side, I already have d1 that beats this d2 here. And then I'm adding a bunch of d's, which are non-negative. And then I'm adding dk minus 1 minus dk, which is also non-negative. So, okay, so with this situation, with these arguments, what we say is that the induction hypothesis is satisfied for the sequence for d1 minus dk, d2 all the way to dk minus 1. Therefore, there is a graph gamma prime with v prime, e prime, with such that gamma prime has no loops. And you have v prime equals, let's say, v1, blah, 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 vk minus 1. And the degree in gamma prime of, let's say, v1 is d1 minus dk. The degree of v2 is d2. And all the way, degree of vk minus 1 is dk minus 1. So what we have here, we have v1, v2, we have vk minus 1. The degree here at vk minus 1, this is okay. All the degrees here are fine. The degrees here, this one is dk minus 1, this is degree d2. But the degree of v1 is not what we wanted, and we have no vertex vk. So what we do now, to this graph gamma prime, add vk to gamma prime and make it adjacent to v1 by dk edges. So now we are going to add the vertex vk here, and here we put exactly dk edges. And what does it do? Well, that changes the degree of v1 in the new graph. From d1 minus dk plus dk, it becomes d1, and it makes the degree of vk equals dk. So that's the argument here. And there's so we had the case d1 minus dk is positive. The second case is it's actually easier. d1 minus dk is 0. Recall that for us, we had that d1 was greater or equal to d2, greater or equal to dk. And in this case, we have that d1 equals dk, the largest equals the smallest. So this implies that these two conditions imply that d1 equals d2 equals all the way to dk. Okay. So what do we do here? Now we look at the same sequence, but we look at the smaller sequence. We look at the sequence d2, d3, all the way to dk minus 1. And because all of them are equal, so we had before that the sum from j equals 1 to k of dj was even. But what is this sum? This is k times one of these d's, let's call it d1, is even. Now the sum of d2 to dk minus 1, what's the sum there? We have k minus 2 entries, and we multiply by d1. So this is k d1 minus 2 d1. So it's also even. So this is even, implies this is even. So I want to show that this sequence, there is a graph with this sequence. And the other one, because they're equal, the second condition is easily satisfied that d2 is less than or equal than d3 plus blah, 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 plus dk minus 1. So that's true. So by induction hypothesis, is satisfied for this sequence, for the sequence of d2, dk minus 1. Therefore, there is a graph, and I'll just draw it here. You have all these, vertices. This one has degree d2, this one has degree dk minus 1. And so this is from the induction, you get it. And then what do? We add a vertex v1, we add a vertex vk, and between them, we put as many as d1 equals dk edges. And that's the graph that we want. All right, so that takes care of this part. So let's go to the, I think the nicest part of this story is when you have the most restrictions. So we want no loops and no multiple edges allowed. Okay, and now this is a theorem, and I gave you there the paper of Havel from 1955, which is in Czech, but you can see the formula and it will look similar to what we're doing now. And Hakimi, so this is usually called the Havel-Hakimi theorem. And we have, as before, let n be a natural number. And I need them order. So D1 greater or equal to D2 greater or equal to Dn be a sequence of non-negative integers. Okay. So the statement is there exists. So there is a simple graph. So that's what we mean by no loops and no multiple edges gamma with vertex at V and E such that the set V is V1, Vn. The degree of Vj equals Dj for any j between 1 and n, if and only if. So this is a recursive procedure. If and only if there exists a simple graph, gamma prime, with degree sequence of the following form, d2 minus 1 all the way up to dt plus 1 minus 1, dt plus 2 all the way up to dn, where this t just denotes the integer d1. So here, there's no, the handshaking condition doesn't appear in this situation, but there is a restriction. Essentially, it says that if you want to verify that a sequence of n non-negative integers is a degree sequence of a simple graph, okay? So here we have n numbers, then that's equivalent to verifying that the sequence of n minus 1 non-negative integers here is, there is a simple graph with that degree sequence. Now, where do these values come from? So let me explain you that, and then I'll finish up, and we can finish the proof next time. So here's it comes from. So let me give you this implication here. This is the easier one. If I have a graph with this degree sequence, then this graph has some vertices here. Let me call this V2 all the way up to, so they're a bit different. So I have VT plus 1, then I have VT plus 2, all the way up to Vn. And the degree of vertex V2 is D2 minus 1. The degree of vertex here, Vt plus 1, is dt plus 1 minus 1. And the other ones stay the same, dt plus 2 all the way up to Dn. So we assume that there is a graph with this degree sequence. So we have it here in blue, okay? And then what do we do? So we have this graph here. This is its vertex set. And from it, we add a vertex to it. We add a vertex, which we call V1, and we make it adjacent to V2 all the way up to Vt plus 1. Okay. Now, recall, what is T? T is this D1. So now V1 is adjacent to 2 all the way up to T plus 1. So that ensures that degree of V1 is going to be T, which is D1. And these degrees, these minus 1s from here, they are all going to increase by 1, and they become the numbers that we want, D2 all the way up to dt plus 1. So this is where the necessity condition comes, and I will prove in the next lecture why this condition is, so this is the sufficient condition. So I will prove why it's also necessary for the existence of a graph with degree sequence D1, D2, Dn. And next time I will do some examples of how you can apply this. So this is it gives rise to a recursive algorithm to check if there is a graph with a certain degree sequence.